So in the last class, in module 2, we looked at different attributes of turbulence. We started with irregularity, we looked at diffusivity, large Reynolds numbers, and three-dimensional vorticity fluctuations. 4 attributes. The fifth most important attribute, one of the more important attributes, a fifth attribute, is dissipation. So turbulent flows we know are dissipative. Okay? They tend to be dissipative. The kinetic energy, and what is dissipation? The kinetic energy basically gets converted to heat due to viscous shear stresses. You will have the turbulent flows that die out quickly if no energy is supplied. It needs a continuous supply of energy. So the viscous shear stresses perform deformation work. They perform deformation work which increases the internal energy of the material, of the fluid, at the expense of the loss in kinetic energy. That's what happens with dissipation. Now, if you take a random motion, they do not have as much viscous losses, such as random sound waves as an example. They will look random, they look chaotic, okay, and so they might be irregular, but they will not have dissipation. So they do not have viscous losses. So you have flows, turbulent flows, where the viscous stresses are doing deformation work, and that is leading to the dissipation. Now, if you do not have a continuous supply of energy in turbulence, you cannot make up for this viscous losses, right? Because all the energy is eventually going to be converted to heat or internal energy due to the viscous work. And eventually the turbulence just decays completely. So unless you have a continuous supply of energy, the energy is just going to completely die down, decay because of viscous work. So for turbulence to remain, you will need to have a continuous supply of energy. So that's what we mean by that. The major distinction between random waves and turbulence is that waves are essentially non-dissipative, though they are dispersive. Dispersive means they have fluctuations, irregularity, while turbulence is essentially dissipative. Examples of non-dissipative flows, non-dissipative examples would include random motions such as gravity waves in planetary atmospheres and random sound waves, acoustic noise. They are extremely dispersive. They look chaotic, but they have insignificant viscous losses, and therefore they are not turbulent. So that's an example of dissipation, another important attribute. So 5 main attributes: diffusivity, irregularity, large Reynolds numbers, 3-dimensional vorticity dynamics, and dissipation. Okay, the 5 main attributes of turbulence. There are some other attributes that we can focus on as well. One is continuum, and continuum has to be mentioned because we are dealing with fluid flows. The continuum hypothesis is always there. It might seem trivial, but it still has to be mentioned as one of the attributes. Continuum hypothesis I have described already. It refers to the fact that we are not looking at molecular scales. We are looking at macro scales, fluid particle scales, where the scales under consideration are still much larger, much larger than the molecular length scales. So, for example, if you look at the Knudsen number, is an example that determines whether the continuum hypothesis is valid or not. The Knudsen number is a ratio of mean free path to the characteristic length scale. This number has to be much less than 1. So Knudsen number, which is equal to lambda over L, has to be much less than 1. Then the continuum hypothesis is valid. continuum is valid. Another attribute not talked about enough, one of the attributes that is not talked about enough, is the fact that turbulent flows are flows. What does that mean? Turbulent flows are flows. What we are trying to say is it is not a feature of the fluid. Again, let me be more specific. It is not a molecular property. It is a flow property. So essentially most of the dynamics of turbulence is the same in all fluids. It doesn't matter what the fluid is. It can be a liquid, it can be a gas, it can be an extremely thick liquid, it can be an extremely thin liquid, it can be any kind of gas. As long as the Reynolds number is large enough. Again, Reynolds number is a property, is a flow property. Yes, it is dependent on the viscosity. But that Reynolds number alone determines whether the flow is turbulent or not. So turbulent flows are flows and they are not, it is not a turbulent fluid, it is a turbulent flow. The major characteristics of the turbulent flow are not controlled by the molecular properties in which the turbulence occurs. And again, just to describe this even more, since the equations of motion that we saw earlier, the Navier-Stokes equations, since they are nonlinear, each individual flow pattern has a certain unique characteristics, okay, that are determined by very specific initial and boundary conditions. That is a function of the flow. So no general solutions are available. You cannot have a general solution for a turbulent flow. So which means every turbulent flow is different. It doesn't matter what the fluid is, right? They are flows. Turbulent flows are flows. It is not a feature of the fluid. So that's what we mean by that. So if you have the characteristics of turbulence, they depend on the environment. It does not deal with all kinds and types of flows in a general way. We don't have a theory that deals with all kinds of flows. What we do is we try to focus on a family of simple kinds of flows. For example, flows with similar boundary conditions, say boundary layer, say jet flows, say wake behind an object, turbulent wake behind an object. I'm showing here and I'm illustrating here a figure where you have the flow around an automobile. This is typically what you would do in order to understand the aerodynamics of a car. So what is shown here are vorticity structures that are formed due to the flow over a car. So this is a bluff body that creates the kind of flow structures that you see in this figure. What we try to do to understand this kind of flows is look at fairly simple flows, say flow over a cylinder, to try and get a better understanding of that. This is because you cannot have a theory that deals with all kinds of flows. So that is why we tend to focus on families of flows with very simpler boundary conditions. So that takes us to the methods of analysis. So now we have looked at the different attributes, and the two additional attributes, in addition to the five main, the two additional attributes we looked at was, one was continuum, the other one was related to the fact that turbulent flows are flows and not fluids. So that takes us to the methods of analysis. So again, this links very well with what I was trying to say earlier. You cannot have a general solution for turbulent flows. So that's what we mean by that. No general approach to the solution of problems exists. We have equations of motion that have been analyzed in great detail, but you can still not make accurate quantitative predictions without relying on some kind of experimental data. And this again ties in with what we were discussing in module 1, where we looked at the 3 different eras in which physicists have looked at turbulence: the statistical, the deterministic, and the structural. So you will need some kind of experimental data to back your theory, because everything cannot be described by a theory. Again, the next point here, statistical studies, right? That is the statistical approach. The statistical studies of equation of motion you will see, we will actually derive the statistical form of the Navier-Stokes equations, the mean of the Navier-Stokes equations. In such a scenario, you will have more unknowns than equations, and that leads to what we call the closure problem in turbulence. You will have terms that cannot be described. Then you will need assumptions for that. So that comes about as when you try to take an average of the equations. So empirical data is required. At the same time, if you try to draw statistics, if you try to draw the mean, the equations will lead to a point where there are unknowns, more unknowns than equations. Then you will need assumptions for that. And again, this has led to scientists, talking about, coming up with ad hoc assumptions just to make the number of unknowns and equations the same. And some have been successful, but the success of those attempts, it depends on where the assumption is coming from, right? So it strongly depends on the inspiration involved in making a crucial assumption. We'll talk about some of the assumptions as well. So in order to gain a better understanding of this, what we must be willing to do is to use simple physical concepts, even if it means trying to understand a fairly simple flow with simple boundary conditions. And we have to try and bridge the gap between equations and actual flows. So according to Tennekes and Lumley, what we need is spirited inventors just as badly as dedicated analysts. And according to them, the model need not be complete, but it can still be useful. And again, even to this day, no model is complete. However, there are models that are still being used to date that have very ad hoc assumptions that work reasonably well, that give us a good understanding about turbulence. So that's what we mean by it can still be useful. It doesn't have to be complete all the time. Case in point, the eddy viscosity hypothesis, molecular versus eddy viscosity. I have talked about this. If I look at the Newton's law of viscosity that deals with stress versus strain, I have tau is equal to mu du dy. Analogous to that, Bisunas came up with a hypothesis where the turbulent stress is proportional to the average rate of strain. So mu t times du dy average, because now we are talking about a turbulent flow. So the rate of strain has to be averaged. So look at the analogy. Molecular viscosity and turbulent viscosity. Molecular viscosity and turbulent viscosity. So the idea was there is an analogy between those. He himself warned that it might not be correct. So the idea was based on the resemblance between the way molecular motions transfer momentum, right? Because of that resemblance, it's a superficial resemblance. Superficial resemblance between the way molecules transfer momentum and heat, right? As they collide with one another, it transfers energy from one molecule to the other. So resembling to that, similar to that, is the way the turbulent velocity fluctuations transfer these quantities. So as a fluid particle goes from one point to the other, it collides and transfers mass, heat and momentum to another fluid particle. That was the analogy. Although this is not how fluid particles behave. On the molecular scale, yes, that is how it behaves. So another similar theory would be in the mixing length theory, right? There, the analogy was drawn between mean free path and kinetic theory of gases. So the mean free path is where a mean free path is the distance one molecule has to travel before it collides with another molecule. So the average distance between two molecules. The mixing length theory was that transfers momentum, one fluid particle transfers momentum to the other, the distance that it travels, in order to diffuse its velocity fluctuations. That would be the mixing length. So both of these, the eddy viscosity hypothesis and the mixing length theory, are cases in point for theories that are that bring in ad hoc assumptions, but still have given very reasonable predictions for turbulent flow over the years, especially the eddy viscosity hypothesis. To this day, large eddy simulation has exhibited to be a powerful tool for predicting turbulence, and the eddy viscosity hypothesis is at the center of it. So that's what we mean by spirited inventors. The model may not be complete, but it can still be useful. An additional point that I want to show here is, the eddy viscosity hypothesis brings an analogy between eddy viscosity and molecular viscosity. Molecular viscosity is a molecular property. It's a fluid property. This ties in, it contradicts with one of the attributes of turbulence, stating that turbulent flows are flows and not fluids, right? It's not a turbulent fluid, it's a turbulent flow. When you're using an analogy from molecular viscosity, when you're using a quantity like eddy viscosity, which is analogous to the molecular viscosity, a molecular property, a fluid property, to describe turbulence, you are kind of violating that particular attribute. So that's an additional point I wanted to mention. Other methods of analysis, dimensional analysis, and the basis you would have learned in fluid mechanics, the Buckingham-Spy theorem. Here, again, but dimensional analysis has a huge role to play in understanding turbulence. One of the most powerful tools, and the idea is some aspects of turbulence you can learn it purely through a few independent variables. And in such situations what happens is those dimensional methods often dictate the relationship between dependent and independent variables. So if you non-dimensionalize it, you can actually try to understand something from the structure of turbulence. An example is the inertial subrange of the turbulent kinetic energy spectrum. I will show that through a picture in a bit in the next slide, but just hold on to that thought. The inertial subrange of the turbulent kinetic spectrum is something that we can get through the dimensional analysis. Next point, the asymptotic variance. Turbulent flows in general, obviously we know they are at high Reynolds numbers. That is one of the attributes. So the proposed descriptions should behave in a proper manner as the Reynolds number tends to infinity. An example of that is the Reynolds number similarity in turbulent boundary layer. Remember, here when we are talking about the Reynolds number similarity in turbulent boundary layer, we know that turbulent flows tend to be almost independent of the viscosity as the Reynolds number keeps increasing, right? So at very high Reynolds numbers, all turbulent flows look the same. And when I say look the same, we will look at certain specific quantities and you will see that those quantities behave in a similar way. So that asymptotic invariance is what we are saying. They tend to have an asymptotic behavior as the Reynolds number tends to infinity. A simple example would be there might not be any difference in the flow when you look at the Reynolds number if the flow of a jet hypothetically is between the Reynolds number is 1 million or 2 million. just as an example. When the Reynolds number is that high, when it tends to infinity, the flow tends to be similar. Okay. Local invariance. So local invariance is again another method used to analyze. The fact that it exhibits a local invariance can be used as a method of analysis. That is what all these are. The characteristics of turbulent motion at some point in space and time appear to be controlled by the immediate environment. And it is dynamically similar everywhere if you non-dimensionalize it with the local length and time scales. So the picture here shows how we can use scaling laws, okay, and non-dimensionalize it. So that has to do with dimensional analysis as well, and the fact that it is locally invariant. You can use scaling laws to try and draw a similarity between different kinds of turbulent flows. So what is shown here in this picture is a turbulent energy spectrum. Okay. Some of these quantities we have not dealt with, but for now, just understand this picture as being as a turbulent energy spectrum. You will see that on the y-axis, I have an E11, indicating that it is a 1D energy spectrum. Okay, so it is only taking the energy due to one velocity component. For now, just keep that in mind. It is taking the energy due to one velocity component and it is taking the spectrum of that. It looks like it is divided by a set of components. How did we come up with these components? We will talk about this in detail in the next module. Again, for now, just understand that that energy spectrum has been divided by a quantity such that this entire thing on the y-axis is non-dimensional. Similarly, on the x-axis, I have wave number, kappa, and multiplied by eta, which is the Kolmogorov scale. I will describe all these quantities in the next module. But for now, just understand that the x-axis and y-axis are non-dimensional. So I have used very specific scaling laws to non-dimensionalize the x-axis and y-axis. So the x-axis and y-axis are non-dimensional. Not only that, I'm not just arbitrarily bringing up some quantities. These are very specific scaling laws that match with what is being plotted. And if you see, I have a whole set of data that is there. All of these are experimental data. And I know the legend is not very clear, but understand that there are multiple sets of data here. 1, 2, 3, 4, 5, and 6, say, for example. All these data are from different kinds of flows. Some are from jet flows, some are from wake flows, some are from flow over a cylinder, flow over a flat plate. So different kinds of turbulent flows. All are turbulent, by the way. And what you will notice is that except for the initial part, there is a complete overlap of the data. Towards the right of the curve of the plot, there is a complete overlap of data. So that invariance is what we are talking about here. That is that local invariance that we are talking about. We used dimensional analysis. We used certain scaling laws to demonstrate the fact that turbulent flows are invariant if scaled by the right quantity. If scaled by the right quantity, the non-dimensional value is invariant, as you can see. So no matter what the data is, as long as the flow is turbulent, they completely overlap on the right. And that is what I mean by local invariance. So we looked at these different methods of analysis, right? We started with dimensional analysis and we will see examples. So I had asked you to hold on to that thought. The inertial subrange is something that I had mentioned there. The inertial subrange of the turbulent kinetic energy spectrum. This right here is what we refer to as the inertial subrange. How do I know that? Again, the description of that will come up in the next module. But keep in mind that that inertial subrange overlaps entirely no matter what the flow is. And this is if scaled with the right thing. If scaled with the right quantity, we non-dimensionalize this energy spectrum to come up with plots that look like this. So methods of analysis include dimensional analysis, asymptotic invariance, and local invariance. And the turbulent flow exhibits that. And you can gain a lot of understanding of the flow by scaling it the right way and trying to demonstrate these kind of properties. In the next class, we will look at the origin of turbulence and we will start to focus more on the diffusivity of turbulence. Thank you.